Hello everyone. In today's episode, we're going to discuss an extension that enhances our state monad in order to be able to support yet another very powerful feature, which is error management, custom error management. So record that the state monad is a reset sense, the type that we can see here selected. It's a function. We start with a state S. The state doesn't change in this instance of the state monad, and what we get back is a pair. The pair has two things. Now, let's begin with the right side. On the right side, we get the new value of the state, and this state goes in, state goes out. It's kind of similar to a mutation to the memory, for example, or the context of your program that changes as instructions are executed. The actual output, the actual result of running this stateful program is the A. So you could imagine that you have one result, which is the new state, but that stays underground, and a more explicit result, which is A, which is whatever comes out of the current instruction. The rest is mostly bookkeeping. I'm now going to extend the state monad by adding another parameter, E, which represents errors and error management, and I'm going to state that after we give a state, we either get the pair, AES, or we get an error. Obviously, I have to do a lot of bookkeeping to add the proper signature to all the instances where we have a state monad. It's not very difficult, but it's just a bit of work. Notice also that we have a generic argument extra, obviously, which is the E everywhere, all the places where we have the conversion, where we extract the underlying function from the state, embedding the state data from just the underlying function. Though those things are pretty easy to fix until we get to the first almost tough cookie, which is map state. Now, first of all, we have a choice. Where do we put the E type argument? And well, you know that this is the proper signature of map state, and it's this argument here, the A, which turns into B, which is the proper monadic, or in this case functorial argument. S and E are kind of fixed, are kind of constant. So that's we say that's the type of the state, and that's going to be the same type during the whole computation. And the same applies to errors. This is the kind of errors we produce. So the E goes next to the state because these are the constant type parameters, whereas the A and B are the variable ones. Okay, and obviously now we see here right away that, well, P.F returns an either pair, ASE. So, well, map pair just doesn't cut it. Because we're mapping, well, if we get the pair, then yes, that's what we do. We just turn the A into a B and keep the S to the same. But we have to be careful with the brackets now. Yes, on the right side of the either, we have to turn an E into an E, and well, why would? And if you want to be precise, that's what we have to say. We simply say that, okay, if we're mapping, and we're mapping this stateful computation P, and if the stateful computation is the left side, then it's the pair. So we got an extra result, A and a state. There's ducks outside. So we say, okay, the result goes from A to B via F. We don't know what A is, we don't know what B is, but thankfully F knows what to do with them. And then here, the state stays the same, because mapping does not change the state. That's very important to actually have a proper functorial mapping. On the other side, map either also takes care of the fact that we might actually be encountering an error. And if we had an error, then, well, we don't have an A to be turned into a B, we don't have a state, so we simply just propagate the error out exactly as it is. Next step, the monadic unit. Okay, so for the monadic unit, obviously we have to embed in the proper type of the state. Now this is actually quite easy, because instead of returning the pair, we just embed it into the left constructor of the either, which makes sense because this is the pair, and inler just puts it into an either of pair AS or E. But yeah, we're obviously not going to give an error here. Oh, I see, it's unhappy. Why is it unhappy? Huh? Why would you be unhappy? What's missing a comma? Oh, we're missing a bracket here. Yes, okay, cool. And we now move on to the monadic joining. Now, join is, well, the most difficult operator. I don't think I need to explain why. Okay, so we get a very similar problem now here, because in the previous instance, after running the first iteration of x, so we have to kind of run x twice. The first execution is going to produce, well, did produce a pair, so we would just map the pair, extract the lambda, keep the same state, and then join the pair together. Unfortunately, now this approach is not really going to work, because what we get is the either that contains either the pair with the new state and the s, and those have to be mapped together, or the error. So I'm going to say that we get the pair or error, and I'm going to return null exclamation mark. Yes, okay. So let's recap here. Let's be verbose. Here we get an either of pair as or the error. Yes, is that the case? Oh, no, that's so not the case, because the a is this state. Yes, cool, okay. What we are supposed to return is we're supposed to flatten this into, this might take a couple of attempts because this is really tough for me as well, but I would expect that here we get either pair ase. Okay, so that's the proper flattening. So this is just the result, let's say the tail end of the monad, and this tail end we have to somehow find a way to flatten this state and this stateful computation into just a pair. Now, fortunately, the intuition is easy. It's the same intuition, but if the either is the left side, then we have to turn this into this pair. That's roughly just, well, you might think it's an application, and obviously the error just stays the same. But this is not entirely true, because this pair, we can put this s into the state, but what we get is another either. So now we get an either inside an either. Now let's get as far as we can. So I'm going to say that temp1 is going to be, well, obviously map either. And what do we expect to do in the first iteration? Now these are the inputs. Okay. And the outputs that we want to get, AA1, so no. Now the transformation that we expect is we want to get to this pair. That's our wish, right? One could say, okay, the second bit is clearly IDE, but this first bit, that's very tough, because there is no direct way of going from this pair state into pair, because whatever we do with this combination, we try to join them together, whatever, we could follow the same path as we had before. So first we extract the function from the state, and then we give the identity, and then we apply, but that's not going to work, because this is going to result in an either inside an either. I'm going to forego this annotation because it's actually very cumbersome, and I'm going to say that I want to map the pair, and the right side is going to be the identity over the s. Yes. And on the left side, I'm going to extract the function from the state. Now this bit is certainly going to need some annotations, so let's try to type them. We know that well, it's AB into A1 B1, so the first element S, the second element remains S. I'm being a bit cheap here, starting with the easiest bit. So I have in this pair have this state here, have a state in S, and I want to extract the function, and the function we know looks like this. It's a bit of a pity that TypeScript has some amazing functionality, but the type inference is still definitely not up to par. Okay, and temp1 is now a function that goes from the big either that we have, into the either, where the first element is now simply the extracted thing. Okay, and well, after this map pair, we could say, okay, you know what, then just apply these two things together. I mean, that's most definitely possible, and stronger yet, you know what, there you go, get PE, because that's the input. So let's see what temp1 now is, and there you go, that's the either inside an either. So recall that either is monadic. It's actually monadic twice. Either the left side is monadic or the right side is monadic. It means, being monadic, that there is a join operator for both the left and the right sides. And we've actually kind of seen this already, because we've seen it for join option when we defined that join option was just either where the left side was unit. So in this case, this was the join right, but we need the join left. Okay, so I'm going to copy this, and I'm going to define join either left, and we have A and B. We have now either of either AB, B, right? Yes, and this gives us an either AB. Now, so if the kind is left, then we simply return x dot value, because if the kind of either inside either is left, then we have this, and that's exactly the type of the result. Otherwise, we have a B. We can say inner of x dot value, and the very same thing happens when doing a join either right, which now takes A and either A or B. Now these operations are actually quite trivial, because how many values can possibly be contained in here? We can have an A here, or a B here, or a B here, and so we're just condensing these two cases, and here we have to do the same. And I'm kind of hoping that just by saying in of x dot value, yes, that's going to be alright again. Okay, not entirely sure I like this. Yeah, okay, that's fine. That's okay. We can survive it. I'm going to skip the fact that join option should just be join either left, no, join either right in our case, because I want to jump right away to the fact that this temp1 either blah blah, I can pass it through join either left, and well, let's see what happens. Temp2, that's neither pair ASE, because well, temp1 might have two errors. The first error, which is the outer one, it's actually the second left to right, is the one that might have come from the first iteration of the first layer of x. It's this first state. But obviously also the second one might have failed, and ultimately for the final result it doesn't really matter which one failed. We got an error at some point, and that's what we have to return. So there you go, that's temp2. Now we know that we can just return this in our eternal quest for the for that one-liner. But obviously we could also just return this instead, and right after computing it, we can simply join either left. And because this is now just a lambda that takes as input PE and returns well, this big thing here applied to PE, we can simply return the lambda directly. Let's see, yes, and now it's happy. And now notice that this map pair, it's still there. It's still very much there, but because our thing is encapsulated in another monad, and pairs are not monads, eithers are, then we see that this nesting of monads requires a nesting of operators. That's very elegant. It suggests that monads are somewhat composable, but not as much as functors. Okay, then we have then state. Then state is just a half operator, you could say, because we get it for free from the rest. Map state SE and join state SE, because we know that map state, so map F, then join F always gives us the then operator for free, and we're done. Oh wait, I see maybe another error. Yes, SE. Okay, and now it's happy. Well, obviously our previous example isn't happy, but we're going to work on that in a second. Now let's move to our example. In our example, let's say that our memory, well, is as the type. Memory is a map. Do we have a map? By the way, let me check if I've imported something. No. So let's import map from immutable. Yes, we are lucky. Okay, so yes, this is a map from the name of the variable into. I'm just going to say that everything's a number in this program. Okay. And errors are just strings. Or no, let's say that we want to be more specific. Not found. Let's say that not found or division by 0. Okay, it's not the best taxonomy of errors, but bear with me. Okay, so now we have S and O. Well, this obviously now we have a fully extensible let's say memory system. So now we're actively forgetting about type safety. So when we get a variable, then well, we know what the state is, and we simply get a name of a variable. Okay, and this gives us a state of memory, error, and number. Now, well, this is not entirely true, obviously, because we can't really get memory from a variable from S0 before knowing that it's actually there. So we're going to check whether or not S0 has the key. And if that's the case, okay, inl, which just gives us the right value, then we get k. And being always careful with the brackets, yes, otherwise we simply give inl with as error. No, oops, not found. Now I get the feeling that it's not happy, probably because something is not typing as it should be typing. Oh, well, have to really promise, yeah, with an exclamation mark that the value is there. I don't know why has and get have not been built. I don't think it's even possible actually with TypeScript. Okay, now it's happy. Cool. And well, setting a variable that doesn't really give us that doesn't run any danger of failing, so it always gives us an inl where we, well, don't give value back, so that's unit, yes. And the first bit on TypeScript is being very generous here, but we shouldn't let him. And then we say that we set k to b. Yes, there you go. Okay, and now what's particularly interesting we can do with our state monad that can fail is we can define a try-catch statement. So we can define our own way. Of managing errors. So let's see. I'm going to put it here. So try-catch. What does try-catch do? Let's define it in our domain. But obviously it is, well, can be generalized. Try-catch gets one of these, which let's give it even a better name. Let's say this is an instruction. It's an instruction or a statement. What do you prefer? Instruction, statement? Instruction. That sounds friendly. Instruction of A is well, better yet, we've decided everything's no. Sorry, no. That gives an A back because some instructions give us a unit, some instructions give us a number. Okay, try catch. What does it get? We try a program, or let's say the body, and that's an instruction of A. But then we also have the fallback, and the fallback is the, well, let's say the catch. We could say that the catch gets as input an error, because then we have an error and we could react differently to different errors. And this error, and after this error, we return the instruction of A. This gives us back an instruction of A. Let's return Alex language mark to see the red disappearing, and it isn't. What have we done wrong? I'm mildly surprised by this. Yeah, obviously A doesn't exist yet. Did we miss? Now I'm going out on a limb here and say that this is the problem. Yeah. Thanks for the great. What's the error it gives? Expression expected. Thanks. How about saying that catches a reserved keyword? Okay, so on error. There you go. Okay, alright, cool. So now we have to give back an instruction, but now I'm going to, how can I say, take charge. We know that the instruction can be built as an instance of the state monad, so I'm going to say state from fun because I really want to define my function. I take as input our memory m. I'm going to call it S0 because that's always been our standard, because I really want to see what comes out of the body, because if what comes out of the body is an error, then it's time to run the on error callback. Otherwise we simply give back whatever the instr gave us. Okay, and now, well, I always put return null exclamation mark, because if I have an error in one of the intermediate expressions, then at least this way I can see it. Okay, temp1, and I simply run the body on S0. Okay, then if temp1 dot kind is, well, if it's right, then we have an error, then we return on error dot f called on temp1 dot value, which is the error, and then we call it on, oh, is it happy? No, it isn't, obviously. We call it on S0 on the initial. Oh, I'm missing something. What's F? Oh, yes, obviously. Sorry, there's 2 levels. Otherwise, we simply return. Well, temp1 dot value. Why is it unhappy? This does surprise me a little bit. Well, what's temp2? Oh, that's the pair. No, otherwise we simply return temp1. Yes, there you go. Or if we want it to be, well, like, a bit more annoying, we could say inl of temp1.value, obviously, because temp1 is the whole either, and I can't unpack the either. Or in this case, I'm just repacking it. Okay. You might have noticed that this is a map either, or at least it should be. And this is what we do in case. So we do basically an inl on the left value, and we just do on error, and then we apply it on S0. Actually, let's. Yeah, no. We could leave it here. We could build it with a map either. It feels like, no, let's, yeah, you know what, let's give it a try. Okay, so, why do I get myself into these things? I could have simply said, no, you know what, that's life, we keep it as is. Okay, so we have F, and right after F we get to run map either. Let's say that, well, let's start with the fact that the right side I'm going to keep it easy, whereas the left side I'm simply going to run it on top of inl. Now I'm very curious to see what F is. Okay, so function memory either pair memory unknown. Okay, that looks decent. So now let's, for the right side, simply simulate, no, not that expression, but this expression here. But obviously inside the function, now we don't have access to temp1 yet here, but we know what this value is. That's the argument that's going to be given to the right, let's say, branch of the 3. And, well, getting there, okay. So, but it's not exactly what we need, because, well, map either is a reasonable choice on this side, but if you look at the result, then we're kind of duplicating the either here. Oh well, I could just apply this to S0, then we give it the memory, and then our function f, well, it gives us now an either with an either. Yeah, and then the instruction. Oh yeah, so here we should also call this on S0 again. No, we're missing an F, right? Yes, there you go. And now what we get, and that's interesting, we get we get two eithers here. So and I'm going to lift this because I want to state that this function, or maybe that, well, I'd like to help the system understand that this inla, the B, I don't know if we can give the annotation, I'm doubting. No, that is a pity, yes. But let's see if we get lucky. Yes, we did get almost lucky. I'm wondering whether or not we missed something. Because this inlet here, oh, it's not E, obviously, it's directly error. Yes, we have no E. Okay. Now, and this very complicated construction, now it's particularly interesting because you notice that we have an either where both values are the same. And that's right, because actually what we want to do is we don't want to keep this either. What we've done here is also called a visitor in object-oriented programming, and it's a pattern where we extract the either, we extract the same result from both eithers. Now, ironically, the result that we extract from both eithers here, if you look at it, it's an either per a memory error. So what we really want to do is we want to say, okay, you have this either, but now collapse it. I'm going to introduce another operator, which is collapse either, which has only one generic parameter, takes as input an either AA, and what it returns is, well, just an A, and this is x dot value. Now you could also extend this to something that looks a bit like map either, but now I do really leave this as I leave it as an exercise for you, because having this makes it possible to have what I'm going to describe now. So suppose you have AB and C, and I give you a function A that goes into C, a function B that goes into C, and have an either AB as input, and we want to get just a C. Now you could say first you map, and then you run our previous collapse either. So these two things are isomorphic. They are basically doing the same, even though this would be a slightly more canonical implementation, but this one is exactly the one I need now, so that's the one I'm going to use. Okay, so we are in our definition of F. So if we say, and then, you know what? Collapse, oh, what have I done? Collapse those eithers. And what we get is either per a memory error, which is the right side of the monad that we need, and there you go. And we can just return it, and we're done. And now, oh look, what do you know? Well, we can throw this away. This disappears, curly bracket disappears, and oh, well, that's a bit annoying. Oh, that is really a pity. No, we need the state. I'm not going to fight against having the state disappear, even though there is a way, but I'm going to see that in the next course. So let's keep the lambda here so that we can just use the closure, because if we need to run the error case, then we really need to have the state. And you might also notice that, well, actually there is no dependency on the fact that this type has to be memory, this type has to be error. So we could easily generalize this, and let's do this at this point. We got so far, right? And let's generalize this to our state monad. And now, well, this is a pair of AS, this error is E, and there you go, now it's happy. Okay, so we have our get var. Let's dig out our hello world here. have to be a bit careful because we have to first set the variables. And now we've basically built, you could say, a dynamic language. We really have a simple dynamic language with some primitive error management. And now get x. Get var x and get var y and set var. We have to say where do we want to put it. So that's in x. Set var y and that's x times 1. But let's also use our try catch here, because if variable x doesn't exist, we want to initialize it somehow. So let's try catch our get var statement, and if get var doesn't work, or we really know that the only error that we can get here is really not found, then we want to set var x to 0, and then we don't care about the result for this, and we try again with the certainty. Or nah, you know what? Then we simply return 0. Hey, why is it unhappy? I believe I know why you're unhappy, because we want you to give us a number back. Oh, but now obviously we have to define the fact that our state is memory, our error is error, and the result is a number. Okay, getting closer. Let's see what's happening here. So, oh, now this alone shouldn't work, right? It shouldn't work because it says state memory error unit. Yes, and it should be. Oh, well, let's give it more hints. Let's say this is an error. Are you happier now? Yeah, sort of. And now it says state memory error unknown. Okay, well, that's mildly disappointing. Let's try to help. Hey, what if I tell you you're a number? And that's what then takes. You should just know what the parameter is. Did we forget something? Oh, I know we did, because unit state takes 2 parameters and he is absolutely right. Now let's give it more annotation. Memory error. Yeah, this is proving to be a tougher cookie than I expected. Let's see if it's happy enough with this formulation. Error. Okay, so it wants. Ooh, that's. Oh. I could have gone at this for a very long time before noticing. It wants a fun. It doesn't just want a lambda. Okay. So just out of spite, I'm going to rephrase it so that it doesn't take the lambda, and there you go. Okay. And off we go, and all of these annotations should just be superfluous. Yeah. Oh, not that one. Yeah, we know that when you have this double lambda, I mean, it makes sense from a theoretical perspective to have these pretty things. But unfortunately, it kind of ruins the type inference. So I'm going to say const value is just instead value is, well, this, and now there you go, value 0. Okay, that's slightly prettier. And so now what this try catch is doing is it's trying to get variable x, and if variable x is nowhere to be found, then, well, we set it to 0. We could also say, okay, you know what, don't set it to 0, then in this case we simply give 0 back. And now I'm going to do the same for variable y, or you could imagine I could do the same for variable y, but actually now I'm going to leave this code here, and I'm going to show you that a little bit by the power of functional programming, but also by the immense power of taking charge of what our program and what the semantics of our program looks like. I'm going to say ensure variable exists, and I'm simply going to define a sort of new operator that force get var. I take as input a variable name, and now I get the variable, okay, and if it's not there, I forcibly set the variable to a value of our choice. There you go. And now I can even remove this because it's a bit of a mouthful, and I can simply say force get var x, and with a default value of 0, and force get var y with a default value of 1. Why not? Now I'd like you to reflect for a second about the immense power of what we are doing here, because we haven't just, this is not just a theoretical exercise, or actually this is, but we've taken charge. We've really taken charge of our semantics. Instead of someone deciding for us, you know what, this is what your programming looks like, these are your operators, be happy with it, and if you want it, yeah, be happy with it anyway, haha. No, in this case we're simply defining, okay, I want to have my statements, and I want to have my definition of state, and I want to have a sort of dynamic thing, or you could have a mix of some dynamic variables and some constant variables, whatever, and you can say I want to have errors, I want to have exceptions, or even more actually, and we'll see in the next video how to take even more charge of this, to define what you want, what you really expect from your own abstractions, and then you can define literally your own instructions. No one binds you anymore to what the language defines as being the proper way of managing errors. And I mean, obviously you have a language and it's very powerful, and you'll still leverage it, but as you progress in your career, you'll notice more and more often that you want more, that you want more data, that you want more control, that you want more power, or that you have a framework and you want to force a given standard of behavior on your framework, because this is also a way to say, you know what, I'm going to carve a bit of my language, in this case TypeScript, and I'm going to really carve a little bit of it, and I really want to stick to this way of programming instead of the whole breadth. So I do personally find this absolutely awesome, but what's coming next is probably even awesomer. So thanks a lot for watching, and until the next time.